In this lesson, we're going to define what common tangent lines are and look at the challenging problems that can arise when we work with common tangent lines. A common tangent line is a tangent line that is tangent to two circles at the same time. We're using the word common here in the same way we use common denominator or something in common, where it's something that's shared. So how many common tangents are possible is dependent on whether or not the circles intersect. Here we have two non-intersecting circles, one outside the other. And we have four common tangents. These ones out here that do not pass between the circles are called exterior or common tangents. And these two here that go between the circles are called interior common tangents. But this is what a common tangent looks like. It's a line that is tangent to two circles simultaneously. If the circles intersect, then we only have two common tangents. There's no longer any interior common tangents, just these ones out here. And if one circle is in the interior of the other, then there are no common tangents. You can't be tangent to the smaller circle without passing into the bigger one. There are also two border cases where the circles are tangent to one another, where you have three common tangents or just one common tangent. We want to see if you can figure out what they look like. We're going to focus on problems that use a common exterior tangent line. So here's a picture of a common external tangent to two circles. The circles have center A and B. And again, remember my advice that when you do tangent line problems, it's good to make the tangent line horizontal and put the circles on top of it so it looks like wheels sitting on a road. It helps visualize correctly how the tangent lines interact with the radii. So if I add those two radii to the points of contact, like so, there they are, we know that they are perpendicular to the tangent line, which means that the radii are parallel because we have these two lines perpendicular to the same line. And now if we add the line that passes through the centers of the circles, like so, it creates two right triangles, one inside the other. And because of these parallel lines, these angles match, they share this angle, so this triangle here must be similar to the larger one, and they correspond in the visually obvious manner. So what we have is we have similar right triangles, and this leads to challenging problems because they use both the Pythagorean theorem and the proportions between the sides of the similar triangles. So let's look at one example of a problem like this. In this figure below, the circles have radii 10 and 12 units, and we're also going to suppose their centers A and B are 16 units apart from there to there. Determine the distance from P to the farther point of tangent CT. So we're going to find the distance from P to T. So first let's label all of these distances. The radii were 10 and 12. This distance from here to here is 16. Now we can't use the Pythagorean theorem yet because we need to know two complete sides of one of the right triangles. The smaller one, all we know is this segment here is 10. The larger one, we know a bit of this side, but on the only complete side we know is 12. But we do have the similarity to work with. So I'm going to follow my previous advice and draw the two triangles separately. And then we're going to move the measurements to the separated triangles. So here's what it looks like. The smaller triangle has PA and 10. The larger triangle has PT, which is what we're after, and 12, and then this distance from P to B, which is partially known. We know the 16, and we don't know this part, so I write it as a sum of the unknown PA plus the known 16. Since the 10 corresponds with the 12, the scale factor between these triangles is 10 to 12, which I will reduce to 5 to 6. So the scale factor is 5 to 6. And then PA corresponds with PA plus 16, so I can set up a proportion. 5 over 6 equals PA over PA plus 16. Let's solve that. So I cross multiply, distribute, and get PA has to be 80. So if PA is 80, this length here, PB, is 80 plus 16, or 96. Then finally, to find the length PT, I can use Pythagorean theorem. 96 is the hypotenuse, and I know one of the legs is 12. So I get 96 squared equals 12 squared plus PT squared. I do some calculator work. Subtract 144 from both sides, so PT is the square root of 9,072, or around 95.2 units long.